Welcome back to the Enclosure Institute. I'm Jimmy Budd.
And I'm Phil Taylor. Today's topic is design considerations for reliable seals. As we've discussed in the previous video, your first consideration is most often the compliance standards that your device will need to meet. Knowing which compliance standards you need to meet will tell you a bit more about the level of performance you'll need from the seal you design.
It seems to us that all electrical enclosures need to prevent the ingress of moisture to some degree. Maybe your device will need to meet NEMA 4 or IP68, or maybe it'll be a rating a little less stringent to the ingress of water, but it most likely will never be zero.
And maybe the device will have to pass UL 50 or CSA C22.2. If your device needs to pass those, then it'll be tested for the reliability of the test and for flame retardancy. Once you've established the compliance requirements for your device, you'll be ready to search for sealing designs and gasket materials that have been successfully used to achieve your targeted compliance.
But there are more things to consider. There are a number of environmental considerations. The most basic is whether your device will be used indoors or outdoors. If the answer is both, then you need to be designing for outdoor use, which is always a harsher environment.
If your device will be used outdoors, you'll consider weather factors and design for the extremes to be encountered. If that environment ranges from Death Valley to the Arctic Circle, then your design and materials will need to withstand the wide range of temperatures and weather conditions.
Many devices that will function outdoors are subject to ozone exposure. The detrimental effects caused by ozone are often attributed to the direct sunlight, but ozone can also be a byproduct of the burning of fossil fuels, including coal.
Some enclosures are meant to be used outdoors but are protected in some way by a larger enclosure or a cover that shields the device from direct sunlight and shelters it from rain. Just be confident that will always be the case.
The next consideration we recommend is relative to the compatibility of the enclosure seal with any elements the gasket will come in contact with. If there can be chemicals in the environment within or outside of the device, it's important to know how the sealing material might be adversely impacted by those.
Guides to the chemical compatibility of most gasket materials are available from the materials manufacturers. This is certainly true of Rogers Materials. Additionally, technical support on this and many other topics are always available from Marion and from Rogers by phone, email, and online.
There are many different types of seals and sealing materials that can be used for electronic enclosures. There are O-rings as well as other molded rubber and plastic seals.
And if your volumes will be quite high, form-in-place gaskets may be considered. Typically, these require an expensive investment in the dispensing equipment and the forms that are needed for the application of the liquid gasket material, so they're used less often. But we'll talk more about form-in-place gaskets in a later video.
The vast majority are seals cut from elastomeric materials that are made in sheet form. These are given the designation JMST2 in the UL 50 standard, and these are most commonly cellular or elastomeric foams for their ability to flex, conform, and compress. This is the type of enclosure gasket supplied by Marion with Rogers Materials.
The next consideration for designing an enclosure seal has to do with the enclosure structure. Enclosures themselves are made from a wide variety of materials, from substances as solid as cast aluminum to relatively thin and pliable plastics. Even glass may be part of the enclosure that requires the sealing, as is the case in many lighting devices. Understanding the type of surface and the available torque or pressure that can be applied to the seal affects the type, density, and compressibility of the sealing material.
Let's give an example of how this is important. Consider we're designing a gasket for an enclosure's door with a 2 foot by 4 foot door and a 1/2 inch wide flange all around. That's 72 square inches of sealing surface. If we use a gasket material that has a compression force deflection, or CFD, of 5 psi, you'll need 360 pounds of force to compress the seal by just 25%. That's enough force to bend thin gauge steel. If we deform the door, we end up changing the compression on the seal and will likely have a leak. In this example, it would be important to use a gasket material with a lower CFD. In other words, a material that can be more easily compressed.
When deciding the thickness of a gasket material, the gap between the sealing surfaces and the tolerances allowed for that gap must be considered. Our design recommendation is that a seal should be compressed between 30 and 50% of its natural thickness to achieve a secure seal. The enclosure will need to be able to compress the seal within that range all around the periphery of the seal, even if the two surfaces are at their maximum allowed tolerance.
We also recommend that the width of the sealing surface be at least as wide as the material is thick. More sealing surface is always better than not enough. If your design will permit it, we'd recommend having the width be at least 1.5 times the thickness.
Another element to take into consideration is the design of the mating surfaces. Many are simply two flat surfaces or flanges that are compressed face to face. Another type is called a blade seal, where one of the mating surfaces is a dull, relatively thin protrusion, like the dull side of a knife blade, that will close against the flat flange. These are generally used when the gasket must be compressed much more than 50% in order to seal, but care must be taken so that the blade depth is not so great as to damage the gasket material.
Also, you should consider the purpose of the opening in the enclosure that's being sealed. Many openings or covers are sealed as the enclosure is being assembled and are never intended to be reopened. Others, like access door panels, are meant to be opened and closed repeatedly. Resistance to compression set is important in both situations, but the consideration is magnified when the gasket is recompressed repeatedly. We'll talk more about compression set and other important properties of the sealing materials in the next module.
The final consideration we'll discuss today is relative to longevity and dependability. As we've said before, no engineer plans a seal to fail prematurely. However, many do. We believe a gasket should be designed to outlive the useful life of the components within the enclosure, or at least until the planned time for scheduled maintenance when the gasket can be replaced with a new one. But we also don't believe that the gasket should be so over-engineered that it's needlessly expensive in material and/or die cutting.
At this stage of design, the engineer should ask, what does failure look like? It's one thing for a little dust to ingress into the enclosure if that won't cause the components to misfire or shut down, but it could be quite another problem if the leak leads to a catastrophic malfunction.
The Poron and Bisco gasket materials manufactured by Rogers Corporation are high-performance foams, ideal for predictable, reliable, and long-term service. Marion is equipped to provide these materials cut to custom shapes and sizes with precision, and to provide them in a manner that allows the customer to effectively and efficiently assemble the component into their enclosure.
Our goal is to enable our customer to design and build the best versions of their device with the most cost-effective and efficient seals.
Okay, we'll take our sales hats off for now. Stay tuned for the next video where we'll investigate many of the common or popular gasket materials on the market.
That discussion will not just be limited to the materials manufactured by Rogers. We'll be looking at materials available from many of the leading manufacturers.
That's it for today. Thanks for joining us. I'm Phil Taylor.
And I'm Jimmy Budd. See you next time.